Hello students, welcome back. Let's go to the last topic here, logarithmic scaling. Three previous models are all exponential models, and this one is the only logarithmic models we have here. And logarithmic scaling is defined kind of like this. We can use any base, but typically we use either log base 10 or natural logarithm given by base e. Some coefficient I over I0. I0 is the standard state. Standard state or initial intensity, whatever. One of more typical examples of logarithmic scaling is this example, earthquake model, Richter scale, but there are other models as well, like decibels, that is how loud the sound is, or the looks model, how bright you feel, things like those. And those are because a lot, if not most, of the human feeling are actual logarithmic. And there's a theory behind it, as a matter of fact. People feel the different intensities by different nerve endings react to certain stimulus. And whether one nerve ending, one nerve cell reacts or not is just all or nothing, but it's probabilistical. And probability given by the independent probabilities just keep multiplying, so it's exponential. And that's why humans are feeling most of those stimuli logarithmically. Anyway, the most typical example is Richter scale example. And here we go. The 1906 earthquake in San Francisco had estimated magnitude of 8.3 in Richter scale, which is given like this. In the same year, a powerful earthquake occurred in Colombia, Ecuador, that was 4 times as intense. What was the Richter scale of the second earthquake? The model for Richter scale is as follows. And we have to answer, okay, 4 times as intense. So one for San Francisco, 8.3. So one for San Francisco is 8.3, and this is for San Francisco. And then Richter scale for Colombia-Ecuador border, so CE, is log base 10 of 4 times as intense. So from here, we have to find out this quantity. S is standard here and there, they're common, so they're not going to make too much difference. We don't know this, but we don't really have to know. This one is 4 times as intense. And then as for Richter scale, previously 8.3, and this one we have to find out. And that's how Richter scale and similar kind of logarithmic scaling are working. Okay, ready to go? All right. So let's find this one out. And let's use log rule. Oh, excuse me. Let's use log rule. So if I use log rule, we have multiplication and division here. So it's log base 10 of 4 plus log base 10 of intensity, same as San Francisco, minus log base 10 of the standard case, isn't it? And that's something we have to find out. How about known information? Come on. Log base 10 of, why am I doing this? I can just copy and paste this thing. San Francisco minus log base 10 of standard. So this is what we have to find out, and this is what we know. Can you use this somewhere here? Do you notice? This part here, which I just highlighted in red, is this one right here. .3. So this much here is 8.3. So this is basically log base 10, 4 plus approximately 8.3. All right. 8.3 and all these must be approximations. So let me change everything into approximation here. All these are coming from observations, so I'll have to change everything into Wrigley equality sign. And as for log base 10 of 4, what is it? I have fancy Mathematica here, so I can calculate log base 10 of 4. And then I can ask Mathematica to calculate, and then it is 0.60 something. So therefore this is 8.9. Yeah, approximately speaking, 8.9. You can write like that. Now, if you do not have this kind of fancy calculator, then you can calculate log base 10 of 4 like this. Over ln base 10, and this is a change of base formula, remember? And then use your calculator. Log of 4 over log of 10 using the natural logarithm, and run your calculator and see if you get this. Now, if your calculator already supports log base 10, go ahead and use it. As a matter of fact, if you're using TI calculator, log base 10 is already supported. So you can get this computation done right away. Anyway, here we go, 8.9. Let's see, what did I do in my answer key here? Oh, same deal. So, okay, I didn't completely expand everything here, just took the 4 out, and then the rest I just kept it. So that part here is 8.3 because of this for San Francisco. Either way, I'm going to get 8.9. Okay, so much for logarithmic scale and Richter scale problem. I have a confession to make. I have never written logarithmic scaling problem, especially the Richter scale problem, in any college algebra exam yet. The reason I never had chance is not that this model is less important. You see, early on, I used to write compound interest model to help students getting more familiar with money matters. And then the subprime and the Great Recession took place, and I ended up discussing the debt repayment model a little bit more often because that was hitting students harder. And then Fukushima Daiichi disaster took place, and then I switched my attention over to radioactive decay models. And then COVID, nowadays, I'm discussing more about logistic growth model. It's just that major earthquake hitting somewhere close to here, close to us here in Texas, that's not something I can think of. So it's quite unlikely that I'll end up writing logarithmic scaling model in final exam, especially considering there are other models that are hitting us more directly right here, right now. But then again, who knows? If some headlines on major earthquake hits our attention, and everybody is talking about the earthquakes, for instance. Well, hope not, but if that happens, then I may end up writing some Richter scale problems or things like those in the exam as well. But for now, let's stick more toward the other problems. Let's see, compound interest and debt repayment model, and the radioactive decay model, but most of all, especially nowadays, logistic growth model, especially upon infectious disease, because that's what's hitting us right now, and that's what's affecting us the most right now. Okay, that's it. And everybody, I hope everybody had a great semester. Everybody must have learned a lot, or at least I hope so. And everybody, good luck in the final exam.